This is our PowerPoint about oxidation reduction reactions, often known as redox reactions. For some of you, this will be a familiar old friend. You've done it in grade 12 chemistry. In fact, you've done it in quite a lot more detail than we're going to be looking at it for our purposes. So if this is a brand new topic for you, don't worry, we're just going to kind of get our feet wet with this. Mostly the purpose behind learning a little bit about redox reactions is that we are going to use some of the concepts to help us understand some of our cellular processes, such as cellular respiration and photosynthesis and fermentation and some conversions of materials, i.e. Carb to fat and fat to carb. So we need to know a little bit about this. We're going to spend some time just covering the very basic of basics, and I'll leave the rest of the more detailed work for grade 12 chem when you do take it, if you haven't already. And we'll just kind of focus on the overall ideas of oxidation reduction reactions. So in biological systems, there are three main categories of chemical transformations. Today we're looking at the first one here, which is the transfer of electrons between molecules in what we call redox reactions, and they make up a fairly large portion of our biological reactions, particularly because they are so crucial to cellular respiration, and we understand that cellular respiration is essential to to the life of biological systems. It's a way that we can produce manageable chunks of energy from our larger energy molecules. And the example that I have here is, it's really not a biological example, it's just kind of small and easy for us to see here that maybe we're moving some electrons around. The second kind of reaction we haven't looked at yet either, and that is acid-base reactions, so very common in biological systems. We're going to be spending some time looking at a different PowerPoint on acid-base reactions, where we're going to explore the more organic or weaker acids than you're most likely familiar with. My understanding is that in your chemistry classes you spend a fair amount of time looking at strong acids and strong bases, and we're going to spend a little time looking at some weaker acids and bases and how they can be used as part of a buffering system, which is very important in biological systems. So we need to keep our pH fairly constant, particularly for our protein structure, the integrity of our protein structure. So buffering is very important. We will look at some examples like buffering in your blood to maintain the proper pH and so on. So that's something that's coming up. And we can see a little example here in our graphic of an acid and a base, and then the conjugate acid, conjugate base, and we'll be looking at how those reactions are quite reversible in those buffering systems. The third kind is what we're probably most familiar with, certainly in this biology course anyway. We spent most of our time so far looking at condensation hydrolysis reaction as a function of polymerization and depolymerization, and even in creating composite molecules like our triglycerides, we've looked at condensation and hydrolysis reactions. So that is the one that we're probably the most familiar with, certainly the most recently studied. And here's a little example where we can see, and hopefully you guys recognize these molecules. We have two amino acids here, and they are forming a dipeptide with the peptide linkage in there, and we're removing water. So we're seeing both the arrows pointing both ways, so we see that it's a reversible reaction. We can create the dipeptide, or we can split the dipeptide depending on whether we are removing or adding water. All right, let's look a little bit more closely at redox reactions. So what exactly do the terms mean, or those pieces, oxidation and reduction? So we're going to keep it really simple. Oxidation we refer to when we're referring to the loss of electrons from an atom or ion. Reduction we use to refer to the gaining of electrons by an atom or an ion. So oxidation is loss of electrons, reduction is the gain of electrons. And here's a little acronym for you to maybe help remember it, or sort of a memory mnemonic to remember it. So for loss of electrons, losing electrons, which means oxidation or being oxidized, we use the acronym, or again the mnemonic LEO. And for reduction, gain of electrons reduced, we use GR. And so Leo says GR, which I think is a nice biological way to remember it. If you've learned it in chemistry, you may have also learned oil rig, which is another way that people can easily remember. But I like Leo the lion says GR better. All right, so one of the things that that we're going to look at, again, really briefly, is how to assign oxidation numbers. And this can be quite complicated, and we're going to try and keep it very, very simple. So oxidation numbers give us an understanding of the character, whether it is positive or negative, of an ion or an atom. And there are trends, and please note the trends are not always, they're not sort of locked in, that's not completely fixed, but generally they follow trends very similar to what you would see for the ion forming nature of the elements in the periodic table. So if we have a look at our graphic here, we can see some numbers there that look pretty familiar to us. Again, keeping in mind this time that we're looking at assigning oxidation numbers, these are not ionization numbers. What's not on this periodic table are the oxidation numbers for our transition elements, for our metals in the middle there. And just like when they're forming ions, there are different possibilities for oxidation numbers for those elements. And again, quite a comprehensive study of that, is possible, but we're not going to be doing that for the purposes of this course. All right, so a few more rules. We've looked at some trends. So rule number 1, the oxidation number of a free element is 0. So if we're looking at one particular kind of atom, we are looking at assigning an oxidation value of 0 to that particular atom or diatomic molecule. The oxidation number of a monatomic ion, that is an ion that has only one kind of atom as part of the ion, is whatever the charge on that ion is. So if you're looking at a chlorine ion, so a Cl minus, then the oxidation number for that is -1. So the charge will be the same as the ionization number. Hydrogen is one of our sort of staples. We can almost always count on it being +1, which is great. Very rarely -1. And oxygen is another one of those ones we can count on most of the time being -2. So those are ones we often use to help us calculate ones that we're not so sure on, that may have some variation, that may possibly not follow the trend. Again, the exception for oxygen would be if it's part of a peroxide, which is not something that's going to affect us very much in what we're going to be doing. Just like monatomic ions, polyatomic ions, also the whole ion itself has a total oxidation number of the charge on the ion. That's not talking about the individual oxidation numbers for the components of the ion, but the overall charge for the ion is the overall oxidation number for that ion. And again, if we're looking for sort of not absolutes, but things that tend to hold true most of the time, group 1 group and group 2 elements are almost always that +1 and +2. So we can rely on those fairly often. And aluminum almost always +3. So we can use these values to help us find things that aren't quite so set in stone, things that don't follow the trends, or things that have a variety of oxidation numbers that they. So let's have a look at how we might be able to do that. There are 2 examples in this table. The first example is a compound. And we're looking here and we're seeing that we have potassium, which is in family number 1. And so we know most likely has an oxidation number of +1. We've got oxygen here, which we also know we can fairly, usually count on for being -2. So if that's the case, we can use those numbers to figure out what carbon must be, because even in the trend chart that we looked at, the periodic table, carbon was listed as being +4 or -4, and it's not always either one of those. So we're going to go ahead and try to use what we know with the most certainty to calculate what we have the least certainty about. So in this case, we're going to look at potassium first. We see there are 2 potassium in this compound. Each potassium has an oxidation number of +1 for a total of +2. And overall, a compound will have a 0 oxidation number. And our oxygen, there are 3 of them, and the oxidation number for that is -2, for an overall of -6. So again, for a compound, we're going to have an overall oxidation number of 0. That means our carbon has to make up the difference here, which means that because we only have 1 carbon, the carbon must have an oxidation number of +4 to give us an overall of 0. So we can use our more certain things to help us calculate our less certain things. In the second example, it's actually an ion rather than a compound. So our overall charge has to add up here to be the charge is -1, but our oxidation numbers have to add up to also give us -1. And again, we've got some ones that we're pretty sure about in here. We've got our hydrogen as +1, and we've got our oxygen as -2. And if we do similar kinds of calculations, hydrogen, there's 1 hydrogen at +1 for a total of +1. And oxygen, there are 4 of them with an oxidation number of -2 for a total of -8. And we know that overall the whole thing has to equal -1. So that means our sulfur here, unlike the -2 that we might have expected, is in fact, -2 that we might have expected is in fact a +6 in this case. So again, using the things we're more certain of to calculate the things that we are less certain of. So pretty straightforward math, and we've got a couple of examples coming up for you to try. All right, so just a couple of practice problems here. For the first one, again, we're looking at how to figure out the oxidation number for antimony, and we see it in compound here with oxygen. So pretty straightforward. We know that oxygen, there are 5 of them. We know that each one has an oxidation number of -2 for a total of -10. This is a compound, so we know that overall our oxidation number has got to be 0. So that means if we have 2 antimony, each one of the antimony must be equal to a number that will give us overall +10, so that the whole compound is 0 when you kind of add those numbers together. So my number in the question mark here, of course, is going to have to be +5. So carry on and do number 2 and number 3. And if you're having trouble with them, make sure that you bring them along to class on the appropriate day, and we'll go over them and talk a little bit more about them in class. All right, so now that we've done some practice with signing oxidation numbers, let's have a look at how this can be important, or how we can use this new sort of language, if you like, language of numbers, but this new language to tell us a little bit about how electrons are moving around, and how later we might be able to apply that to our cellular respiration and photosynthesis. So to do that, we're going to have a look at reducing agents and oxidizing agents. So a reducing agent is the reactant that gives up the electrons. So remember, loss of electrons means you're being oxidized. The thing being oxidized is the reducing agent. Maybe an easy way to think of that is that the thing being oxidized is helping the other thing become reduced. That is, the other thing gaining electrons. The thing that's losing electrons is helping the other thing gain electrons. So that makes it the reducing agent. The oxidizing agent then is the reactant that gains the electrons. So by gaining the electrons, it helps the other component oxidize or lose electrons. So the thing being reduced is the oxidizing agent. The thing being oxidized is the reducing agent. And again, the reducing agent contains the element that is oxidized, and the oxidizing agent contains the element that is reduced. Okay. All right, so now we need to put all those ideas together. And to do that, we're going to look at an equation. We can see we've got a balanced chemical equation here. And we're going to look at how electrons are moving from the reactant side of the from the reactants to the products in this equation. So first things first, we need to assign oxidation numbers. If you are going to try to assign these numbers yourself, if you want a little more practice, pause the video and see if you can work out the oxidation numbers and then match them up with what I've got coming up here now. So there are the oxidation numbers for that equation. And now what we need to do is we need to have a look from what's happening on the product side of the reaction to what's happening, or sorry, from the reactant side to the product side of the equation. So if we look here, we're looking for changes. So oxygen, obviously, if we look at the oxygen, in all the cases we've got here, oxygen is -2. So that's not the element that we're interested in, not the component that's going to be changing. So it must be the other two. Remember, if we have something that's losing electrons, we also must have something that is gaining electrons. So if we look at the iron on the left here on the reactant side, we can see that iron on that side has a oxidation value of +3, and on the product side we can see, because iron is all by itself there, that iron has an oxidation number of 0. So that is clearly a change. And if we think about what's happening there, it looks like iron has gained some electrons, gone from a +3 to a 0, and therefore a gain of electrons reduced. That means that iron has been reduced. And if we look at carbon on the reactant side, it's +2 versus carbon on the product side, which is +4. And it looks like the carbon has lost some electrons. So loss of electrons is oxidized. So iron has been reduced and carbon has been oxidized. That makes, or hopefully makes sense for everybody. So again, written out here now, the iron has been reduced. That means it has gained electrons from a +3 to a 0. And that the carbon has been oxidized and lost electrons and gone from +2 to a +4. In terms of oxidizing agents and reducing agents, iron has been reduced, so it is the oxidizing agent, and carbon has been oxidized, so it is the reducing agent. All right, so now that we've run through that, I'd like you to have a look at a couple of other examples. Again, we may see some of these on quizzes or tests, but we're going to keep them really simple with hopefully a lot of things that follow our trends, so they're pretty easy to figure out. So for the examples coming up, I'd like you to assign oxidation numbers to all of the components. I'd like you to then show what is oxidized and what is reduced, and identify the oxidizing agents and the reducing agents. So here's your first example, pretty straightforward and simple one, and a second example. I'd like you to give those a try, and again, bring them into class with you on the appropriate day if you're having some difficulty with them, and we'll be working on some more examples altogether. Okay, ladies and gentlemen, that is it for today.